5.3 follows very nicely after 5.2. In fact, it's going to seem like basically a carbon copy of 5.2. Obviously it's different because 5.2 was about arithmetic sequences in series, and 5.3 of course is on geometric sequences in series, but this section 3 is going to seem very, very, very similar to section 2, because we're going to be doing the same kinds of things, following the same format, same kinds of problems, and all that jazz. But here we go. So I just got done saying that obviously geometric sequences in series are different from arithmetic. So recall that an arithmetic sequence was a sequence in which each term was obtained always by adding the same common difference to get to the next term. Like you were always adding the same thing to jump from term to term to term. Well, a geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed, non-zero constant, which we're going to call the common ratio. And, like for example, just got to throw the word non-zero in there because, it's just kind of a technicality, you can't multiply by 0 to get to the next term in a sequence, But anyway, let's focus more on that. Remember, with arithmetic sequences, there was a common difference because we were always adding the same thing. But with a geometric sequence, we're going to say that it's a common ratio because we're always multiplying by the same thing. And we're going to call that R. So the common ratio, we're going to use the variable, the letter R for it. And so here's a few examples as you write those down. Maybe an even simpler example to kind of start off on would be like, 1, 2, 4, 8, 16, 32, 64, and so on and so forth, where you're always multiplying, again, by the same number to jump to the next term. And so again, feel free to pause the video if I end up going too fast. That's always an option on these videos. But the common ratio for this red sequence is going to be 5, because we're always multiplying by 5 to get to the next term. And in the maroon sequence here, what are we always multiplying by to jump to the next term? And 2. We're always multiplying by 2. And the purple one is a little bit more weird, challenging, I guess. What's R? What are we always multiplying by to get to the next term? Like 9 times what gets you here, and then -3 times what would get you there. And it turns out that it's -1/3. So a comment that I naturally think of to kind of add here is just like with arithmetic, you were always adding the common difference, but the common difference was allowed to be negative. With arithmetic, you could have had a common difference of -6. And that just meant technically you were subtracting 6, But that still meant that the common difference was -6. because you were technically adding the negative 6. Same kind of thing here. In a way you are dividing by negative 3 to jump to the next term, but technically you can't say that your common ratio is that you're dividing by negative 3. You still technically have to kind of say that your R value is negative 1/3 because that's what you are multiplying by. So again, there's obviously a easy connection, a very strong, obvious connection between adding and subtracting. And here there's a very, obvious, simple connection, very fundamental connection between multiplying and dividing. But yes, this is what R would be, negative 1/3. And still looking at the basics here of what a geometric sequence is, what if you had an example where you were told that the first term, a sub 1, is 12, and you were told that the common ratio of this geometric sequence was equal to 1/2, and you were supposed to find the next 5 terms. Well, again, this is still the basics of what a geometric sequence is. If that's your first term and your common ratio is 1/2, aren't you just going to multiply this by 1/2 to get the second term? And then aren't you going to take the second term and then just multiply that by 1/2 to get the third term, the next term? And then aren't you just going to keep on doing that, always just multiplying by 1/2 to get to the next term? So then it'd be 3 times 1/2, which is 3/2, and then you would take 3/2, multiply it. So you're always multiplying by 1/2. And I hope, even though you might grab your calculator and just punch this into your calculator, what 3/2 times 1/2 is, I hope you haven't forgotten how to work with fractions and how to multiply fractions, for example. Multiply numerator by numerator and denominator by denominator. And then, a little side note, a little side detail there. You always have your calculator nearby. And then for the next term, you'd have to take 3/4 and multiply it by 1/2 again and get 3/8. And, that's what geometric sequences are all about. Always multiplying by this common, where's my cursor? Always multiplying by this common ratio to jump to the next term. So, just like with the arithmetic sequences, there is a formula, a very simple, sort of obvious formula that would allow you to jump ahead to any term you want, the nth term. It's the nth term formula. So it would allow me, as long as I know what the first term is and what the common ratio is, you could jump ahead to like the 80th term, the 145th term, whatever you want. And this formula makes a lot of sense because, let's say you were, let's kind of go a little simpler. Like, let's say you wanted to jump ahead to like the 10th term. Wouldn't that just mean you were going to multiply by the common ratio 9 times? You were going to take the first term and just keep multiplying by R, but only multiply by R 9 times in order to end up at the 10th term? Well, wouldn't that be like R times R times R times R? So you see how there's like a power kind of thing here? If you were going to multiply by R 3 times, it'd be like R to the 3rd power. If you were going to multiply by R 9 times, it would end up being R to the 9th power. So again, like there's this n minus 1 is in that exponent spot, and it's n minus 1 because, like I just said, if you wanted to jump ahead to term number 10, n would be 10, but you would only be multiplying by R 9 times, hence the n minus 1. And so throwing this into an example, just the 8th term, that's not very exciting. But we can still use the formula, even though we're probably not all that desperate. I mean, it's just the 8th term. It's not like it's the 88th term or something. But of course, the formula still applies, and we're going to use it. Find the 8th term of the geometric sequence whose first term is -4 and whose common ratio is -2. So we're going to use this formula, and we're going to plug in what for a sub 1? Well, that's the first term. So we're going to plug in -4 for a sub 1 because a sub 1 is the first term. And they told us the first term is -4. What are we going to plug in for r? Oh, I don't know. Maybe what they told us was r. Common ratio is -2. And what are we going to plug in for n? Well, we're jumping to the 8th term, so we're finding a sub 8. And so we're technically plugging in 8 for n. And from here on out, you just have to make sure you crunch these numbers correctly. Like make sure you're following the order of operations and all that jazz. So, I mean, the final answer, as long as you're doing it correctly, ends up being 512. You can pause the video if you need a few more seconds, which you probably do, but I'm moving on. And I'm moving on to the next big formula. Again, I mean, like it's follow. I told you. We're following like pretty much the exact same format as we did when we were learning about arithmetic sequences and all the formulas, the two formulas. So here's the sum formula for a geometric sequence. If we wanted to add the first n terms of a geometric sequence, here is the formula for that. Okay, and I know it might look a little nasty, but to me, there's like more good news than bad news, because all I see in this formula is the first term, the common ratio, and the n value. I don't see any like a sub n pieces, like we had to do with arithmetic. And remember how a sub n meant the last term? None of that here, so I think plugging in is going to be a lot easier. Find the sum. Hey, find the sum, so guess what I'm going to use? Find the sum of the first 18 terms of the geometric sequence 2, -8, 32, -128. So, if I'm finding the sum of the first 18 terms, that means n is 18, okay? And so we're finding s sub 18, which is the sum of the first 18 terms. A sub 1, oh, I don't know, it's right there, 2. What's my common ratio, though? They're not blatantly telling you that, but it should be pretty obvious. 2 jumping to -8, which becomes 32, which becomes -128. So the common ratio, the thing that we're always multiplying by to jump to the next term, must be -4. So make sure you write in there a -4, so -4. But, like I said on the last example, make sure you're following the order of operations and stuff. Like, I don't even know if I want to say it out loud, but this would not become a +4 because you're going to want to do the power before you do any of this stuff. So at this point, you probably just want to throw it all into your calculator. And if you have one of those yellow mamma jammas like we're using in 2018, or any calculator like it, I mean, you have the extra bonus benefit of having that N over D button. So you could press that N over D button first, throw all this into the numerator spot, throw all this into the denominator spot. Otherwise you have to remember things like putting parentheses around the entire numerator and putting another set of parentheses around the entire denominator. But whatever, I mean, this is what you get. And hey, yeah, it's a big number. It's a big number. That's going to happen pretty darn easily with these geometric stuff. So anyway, really quick, I have to say this. Your calculator may very well have said something like negative 2.7487 blah, 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 times 10 to the 10th power. Or, you know, negative 2.7487, yada, 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 E10, like capital E10. Sometimes calculators will, they'll use that as a way to, show you scientific notation, like a capital E and then a 10. So if you wrote on a test or something, instead of this, if you wrote it in scientific notation, that would absolutely be fine. Negative 2.749, if you're rounding, times 10 to the 10th power, I believe it would be. Example 5. Gee, still following that format that we followed in the 5.2 notes. Now we're going to do another sum example, but this time they're going to give you it as a sigma. And this is where you don't need to write this down. I mean, you really don't. I'm looking for room here. Now, with arithmetic, if you learn what to look for with this sigma stuff so that you know what you're looking at is an arithmetic summation, you're going to see something like 3i minus 7. Or you're going to see negative 4i plus 1. Or you're just going to see 2i. Or, 5i minus 1. So those are 4 pretty quick examples of what an arithmetic summation would look like. And when I look at all of those with my experience and everything, I just go, oh, that's arithmetic. I already know it's arithmetic, and so if I need to, I can use the arithmetic formula. Just having an I, right? It could have just been, I plus 6, If it's just I, then it's arithmetic, The second you put an I squared or an I cubed or anything weird like a fraction or anything, it's not going to be arithmetic. So these are what arithmetic sequences look like. Summations, rather. Whoa, did you see that? That was cool. And this is what a geometric summation would look like. What gives it away to me is this I power. And but if you have to verify, then you could plug in 1, 2, 3. You could plug in some stuff to just investigate. Is this definitely a geometric series? And it looks like it when you get the first term is 12 and the second term is 24 and the third term is 48. It definitely seems like we have a common ratio of what? Of 2. And since it is geometric for sure, which again, if you train yourself what to look for, then you already know from the start that, okay, this is definitely a geometric summation, and we can totally use the formula. Okay? Even though 10 terms isn't that bad to add up, but it could have been 100 or something. So we can use this formula. We just need to know what a sub 1 is. Hey, we just got done finding that, so cool. So my a sub 1 is 12. My r value is, well, we already kind of figure that out. Our R value was 2. And we're finding the sum of the first how many terms. Basically, I'm asking you what n is. And it looks like n is supposed to be 10. So we're finding s sub 10, and we're going to plug in a 10 right there. And once again, it's just a matter of working that out a little bit at a time, or throwing it all into your calculator at once. Whatever you're comfortable with, just make sure you do it correctly, and that's what you should get. Ooh, I don't think I have this color anymore in the new version. Anyway, 12,276, final answer. Okay. Take a breath here, literally and figuratively. The last part of this section, and this is where we kind of go a little bit, not above and beyond, that's not the way to say it. Up until now, we were basically doing the same song and dance routine that we did in the arithmetic sequence notes. So up until now, the 5-3 notes have been practically a carbon copy of the 5.2 notes. But with geometric series, this is like a pretty major difference between arithmetic series and geometric series. We can actually do some stuff, some real example problems with infinite geometric series. Think about that. An infinite geometric series. Just an infinite series, an infinite sum. Can you imagine like an infinite sum? What do you get when you add together an infinite number of terms? Do you actually get an answer? Or does it truly just keep getting bigger and bigger and bigger and bigger, forever? And here's the answer to that question, those questions, whatever. If you're talking about a geometric series, probably like if you were to think of a random geometric series, you'd probably think of something like 1, 2, 4, 8, 16, 32, 64, 128, yada, 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 right? Or you might think of like 3, 9, 27, 81, so on and so forth. You know what I mean? If you're thinking of a geometric series like that, where your R value is like 2, or your R value is 3, or your R value is 5, you're always multiplying by 5, you're always then, if you're doing that kind of thing, then if you just add up like an infinite number of those terms, it's just going to the word is diverge. That's a calculus term. But yeah, it's just going to keep getting bigger and bigger and bigger and bigger, and you're never going to actually have an answer. But guess what? If you have a certain kind of common ratio, there actually will be a sum, even though you're adding together an infinite number of terms. I know it's weird, but imagine you had a common ratio of like 1/2. Common ratio of 1/2. In fact, let's add to our notes here. Not here, right? Not there, but let's get a different color. R equals 1/2, for example. So if your common ratio is like 1/2, for example, then you could have a sequence, of like 1, 1/2, 1/4, 1/8, right? And so like when you added them together, it would be 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32, 1/32, plus 1 over 64 plus 1 over 128 plus yada, 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 right? And so the thing you're adding is just getting closer and closer and closer to adding nothing, right? And so over a span of like an infinite number of terms, you're going to basically converge on a final answer. Like there's going to be this ceiling, this sum that you're never going to quite be able to reach, because what you're always adding keeps getting smaller and smaller and smaller. And so like there's going to be this sum that you can't simply reach. You can't bring yourself to reach, but you are going to keep getting closer and closer and closer to it forever. And so yeah, you could actually have, and since you keep getting closer and closer and closer and closer to it, in math we say like, okay, if we're approaching a final sum of 4 and we're just going to keep on getting infinitely close to this final sum of 4, we might as well say the final answer is 4. It's like in a way it's like essentially the same thing. When you are getting like infinitely close to some number, you might as well say it's that number. Anyway, that was my little rant. And so basically what this says right here, if you have the right kind of common ratio, basically like anything in between -1 and 1, not including -1 and 1, got to be like strictly in between -1 and 1, like -3/4, +2/5, anything like that, you're actually going to have a sum for an infinite series. And this is the very simple formula to use. Okay? And so here we go. Find the sum of the infinite geometric series. And here it is, 3/8 minus 3/16 plus 3 over 32 minus 3 over 64. So what does that make our common ratio? Because whether or not this even has a sum basically depends on what your common ratio is. And if you can't really do it in your head or whatever quick, you could literally do the second term divided by the first term to figure out what your R value is. So if need be, you could literally do -3/16 divided by 3/8, and you could even use your calculator if you need to. But look at this. I don't need no stinking calculator. But you might have been able to do this in your head. Like 3/8 times what gets me -3/16. And the answer is actually -1/2, which is the correct kind of R value where we're actually going to have a sum. So here we, look at all this. So the infinite geometric series will have a sum, which I already said. Sorry, I was a spoiler alert. Which we can find with the formula. Which formula? That formula. What was a sub 1? Oh, I don't know. The first term right here. 3/8. And my R value was negative. That's right, negative. Oh, what the heck was I doing? Getting ahead of myself? -1/2. And so all you got to do is crunch this out, right? Using your calculator if you have to. But the bottom line is, at the end of the day, calculator, no calculator, the final answer is supposed to be 1/4. So yeah, if you keep adding these together forever, you're just going to get closer and closer and closer and closer and closer, like forever closer to 1/4 as a sum. As a sum. Not the terms. Let me make that clear. These terms are not approaching 1/4. The running sum, you know what I mean? Like when you add these two together, you have a sum. And then when you add this in there, you have like a new updated sum. And then when you subtract that, you have a new, even more updated sum. And then you keep on adding and whatever, and subtracting each following term. And you keep on like getting a new sum, right? So the sum will just keep getting closer and closer and closer to 1/4, but never get there. Like never get there. And so we might as well say that the final sum is 1/4, since we're going to get so close to it over infinity that we can't even really tell the difference anymore. And so we might as well just say that it's 1/4. Cool, huh? But that's the section on geometric sequences and series.